Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks, Adam, and thanks for the invitation. Of course, pleasure to be here. I want to talk about a new paper of mine called Intrinsic Robustness, the Price of Anarchy. Before I get into what the paper is actually about, let me spend a few minutes just telling you about sort of the context of this work. You know, what's the price of anarchy? Why does anyone care about it? And so on. So, something which, of course, is well known to all of you, and you've heard mentioned in dozens of talks by this point, I'm sure, is the idea that in the 21st century, most or many modern CS applications are not being done in a centralized way on a desktop, somewhere, but rather fundamentally involve the interaction between lots of autonomous decision makers who, in general, have conflicting objectives. Right? This became really obvious when the internet came out, maybe 15 years ago, and became widespread. Everywhere you see different flavors of auctions, you see competition between internet service providers, and so on. So it became obvious to a lot of different people around that time that, to model these applications, one very natural thing to think about was non-cooperative game theory, right? That's an old famous field. They've thought about, what happens when you get autonomous decision makers with different objectives together in the same place. You want to predict what's going to happen. Scientists have, in large part, fruitfully used ideas and models from non-cooperative game theory to think about computer science applications. And one thing we naturally inherit from the game theory world, and it's hardly surprising, is that the predictions, so in other words, equilibria, so what will happen with different people with different objectives, those outcomes are not going to be optimal in any sense. They're going to be inefficient in the sense that if you think about any natural objective function, so say optimizing some notion of performance of a system, something like that, you let people just do whatever they want and optimize decentrally, you're not going to do as well as if you were an all-powerful designer with full control over this environment who could dictate what everyone should do. So that's the sense in which I mean game theoretic equilibria are generally inefficient. One example, a little bit more concrete, I'm sure you've heard about the Nash equilibrium, for example. That's just a state in which everybody's behaving in a way in which they don't see any way to improve their utility. So everyone has a strategy you can't improve by unilateral deviation. And so these in general are not optimal. But of course a natural response, at least from a theoretical computer scientist, would be to say, well, so we don't have full optimality, right? So in theory CS, we're very used to dealing with suboptimality. Perhaps all is not lost. Perhaps we can still prove meaningful approximation guarantees on game theory equilibria, at least under reasonably general conditions. Okay? So maybe we can be approximately optimal in a meaningful, useful sense. And so that's what the price of anarchy aims to do, quantify inefficiency. And again, to a theory CS person, it would be the obvious definition borrowed from competitive analysis. So by definition, if you have a game, and I'll give you a concrete example of a game on the next slide, but in general, if you have a strategic environment and you have an objective function, so for example, the sum of everyone's utilities, something like this, you define the price of anarchy as a ratio, an approximation ratio. And as usual, in the numerator is some protagonist, something you want to prove something about. In this case, that would be an equilibrium, something like a Nash equilibrium. And on the denominator would be some hypothetical benchmark, generally unattainable. In this context, it would be what this all-powerful designer could achieve, what objective function they could achieve given full control over the system. So that's what I mean by the optimal objective function value. What could be achieved by an altruistic dictator. And of course, as usual, the closer this ratio is to 1, the better for our protagonist, right? So the closer an equilibrium approximates an optimal solution, okay? And so in general, what's the interpretation of a price of anarchy near 1? Well, generally, it's a good thing, right? It kind of means, even if you wanted to do centralized control, why bother? It basically obviates it. The benefit would be small. And in general, what's nice about the price of anarchy, it often suggests kinds of rules of thumb from an engineer's perspective, in the sense that you might want to design systems which are engineered so that the price of anarchy is close to 1, so that selfish behavior doesn't really impact performance. So for one example is an old result of mine, which says in a network routing context, if you add a little bit of extra capacity to network, you over-provision it by, say, 10% beyond what you, strictly speaking, need to carry the demand matrix, then actually selfish behavior just provably always leads to a near optimal outcome. So this ratio is going to be no more than a factor of 2. And that's something that resonates with real engineers. So if you talk to people who operate networks, indeed they do over-provision the networks in order to get good performance. And this is sort of theory that emerges that backs up those kinds of rules of thumb. So this is sort of the background about what this price of anarchy concept is and why some people find it interesting. Let me make it a little bit more concrete, again, before I jump into this current paper and just give you a concrete example. So what do I mean by game and equilibrium and so on? So this is going to be a routing game. And again, this is sort of a good concrete example to keep in your mind throughout the talk. But I want to say right now, when I eventually state theorems, it's actually going to be much more general than routing games. It's going to be more general than potential games, for those of you who know what they are. They're actually quite a bit more, but I mean, just think about this concretely. So the setup here is you have two players, sort of, maybe me and an opponent. We both start from an origin S. We both want to go to a destination T. Let's say we each have, 1 unit of traffic. We're each picking a single path. So there are 3 ST paths in this network, so we each have 3 strategies. We're each picking one. We want to minimize the time it takes to get from S to T. I want to look at the price of anarchy in this network. And so remember it's a ratio of an equilibrium and an optimal solution. So we have to understand what both of those are. So what's the cost structure? Well, so you have 3 links here where the semantics of these numbers is any player which uses one of those links, that's the cost it incurs while using that link. So those are congestion independent. The semantics of the 2x and the 5x is if x players are using it, and here x is going to be either 1 or 2, then the players using that incur 2x or 5x units of cost. And I've set up the costs here so it's very easy to reason about what an equilibrium will look like. In fact, the zigzag path is a so-called dominant strategy. Both of us would use that no matter what the other player is doing. Why is that true? Well, just sort of think of it from a worst case analysis perspective. I'm trying to pick one of these 3 paths. Well, the worst case for that 2x link is we're both on it, in which case it's 4, which dominates the 5. Similarly, the 5x, even in the worst case, dominates the 12. So if you reason individually and selfishly about this, we're both going to take this zigzag path. As a result, we'll both be on a path that has cost 14, right? 4 plus 10 for an aggregate cost of 28. Now, if there was an altruistic designer who wanted nothing more than to minimize our total costs and could dictate our actions, this is not what that designer would do. The designer would prevent us from interfering with each other and split us on the 2 different 2-hop paths. One of us would encounter cost 14, one would encounter cost 10, on aggregate would be 24. So in this example, the price of anarchy, that ratio would be 7 over 6. Okay, and again, in general, the games I'll be thinking about have multiple equilibria, and generally we're conservative and we just use the worst one, the highest number in the numerator. Okay, so price of anarchy bound applies to every equilibrium. Okay, so that's a concrete example. So any questions about just sort of the background context or what it means or how to think about the price of anarchy? So next up is the new paper. Okay, good. Right, so actually that's what the main theorem is going to be about, is how do you reason about out of equilibrium behavior. Okay, so that's one of the main motivations of this work. Okay, is to relax the assumption that you're at equilibrium. Okay, so we will get there in due time. So excellent question. In fact, people have been asking me that question since 2000, so I'm glad to finally have a nice answer to it. Okay, so what is this paper about? Well, it's about a few things. So here's what it's about in English. Okay, so the next slide is going to be, I'm not going to say technical, but it's going to be a little bit abstract for the few slides after this. So I want you to know what the point of all this work is. I want you to know in English what is the goal of this work before I jump into any notation or anything like that. So the first main point is a definition. Okay, what is this definition? It's a sufficient condition for a game to have a bounded price of anarchy. Okay, so it's going to be a definition called smoothness. I'll show you on the next slide. And it will be true that if a game is smooth with certain parameters, it will have a price of anarchy at most some function of those parameters. Okay, sufficient condition for an upper bound on the price of anarchy. The meaning of the definition and the way I sort of came to it, it's meant to encode the usual way we wind up proving upper bounds on the price of anarchy. So it's meant to encode a canonical proof template that generates upper bounds. Okay, so that's the meaning of this. Canonical way of establishing bounds on the price of anarchy. Why is it a useful definition? Okay, which you're really going to be asking once you see what it says on the next slide. Why bother? Okay, so there's 2 reasons. The main reason is that if you prove an upper bound using this sufficient condition, okay, using this canonical template, it turns out whatever number you get, right, if you get a number like 5/2 on the price of anarchy, which purportedly you only were meant to apply to all equilibria, actually that exact same number, 5/2 or whatever, is in fact much more general than you might have realized, than you would have expected. So in fact, in particular to answer Silvio's question, any bound you generate using this sufficient condition will automatically apply not only to all Nash equilibria as you intended, but inadvertently will actually apply to lots and lots of notions of out of equilibrium play. Okay? So the exact same numerical bounds we're all used to, in fact, do not require that the system has converged to equilibria. All you need is that in some sense players are rational. Maybe they haven't coordinated on an equilibria, but they're at least in, say, for example, a no-regret sequence, which I'll give you the definition in a few slides if you don't know what that is. Okay? So the first consequence, if you meet this definition, you get automatic extra robustness with no quantitative loss. So that's the first point of the definition. The second theorem, the second main result I want to mention is that even though seemingly you get lots of extra stuff for free. Seemingly using the sufficient condition seems like it should be much stronger than just a regular upper bound on the price of anarchy, right? Because it gives you all this extra stuff in addition to equilibria. You can actually prove in well-studied, interesting classes that this sufficient condition is guaranteed to give you the right answer, even if you only cared about pure Nash equilibria. Okay? So in other words, there's no loss of generality confining yourself to using this sufficient condition to get the right number on the worst case price of anarchy, even just for equilibria, even if you only cared about equilibria in the first place. Okay? So that's what the rest of this talk is, just translating this into actual mathematics. Okay? But this is what it's about. Okay, so I owe you a definition. And here it is, and I sort of wish I had a whiteboard to put this on. So the main definition's at the bottom, okay, and I want to warn you right now, it's going to look weird. You're not going to know where this came from. You're not going to be able to, it's not going to be obvious why it's useful. It's not even going to be obvious what this has to do with the price of anarchy, although that last question I'll answer on the very next slide, okay? So for now, I just want you to be able to parse this definition, make sure you understand what it says, all right? But let me say the rest of the slide. So it's useful to think about this at a very abstract level. But again, think about those routing games as a concrete example if you like. Think of that in your mind. So, but the abstract setup is you just have a finite set of players, n players. Each chooses one of a finite set of strategies. Okay, so player I is going to pick some strategy S sub I, like a path in a network. Okay, S here denotes a vector of strategies. So that would be a full traffic pattern, for example. The data, which tells us, you know, the input, which describes a game, is just a cost function for each player. You could use payoffs, but I'm going to use costs just for convenience. So we're given, for each player I and each possible outcome, so think of this as each possible traffic pattern, exactly how much player I, what cost it incurs in this outcome. Okay, so that's analogous to a payoff matrix. Secondly, remember we need an objective function to reason about the price of anarchy. So I'm going to make an important, very natural assumption, but this is an important assumption for this theory, which is that we care about minimizing the sum of player costs. Okay, just like in that example in the last slide. This is the most important kind of objective function. It's by far the most common, but the theory I'm going to present does not hold without this assumption. Okay, so this is important. What we care about is minimizing the sum of everyone's costs. So that's the abstract setup. That's all we know. Okay, I'm not going to assume any more domain-specific information until the very end of the talk. Okay, so this is what the theorem's about. It's at this level of abstraction. Obviously, it models routing games plus other stuff. Okay, so the definition is called smoothness. And so again, there's two parameters. So a game, by definition, is lambda mu smooth if it satisfies certain inequalities. And again, depending on the game, you'll be smooth or not smooth for various versions of parameters. So think of lambda here. Lambda here is positive. Think of something maybe like 2 for lambda. Mu here is something less than 1. So maybe think of mu as a half, just to give sample numbers. Okay? And so basically what smoothness is it promises that you can disentangle entangled outcomes. Okay? So let me be a little bit more specific. So it references two arbitrary pairs of outcomes of this game. So say two different traffic patterns, S and S star, which for now have no semantics. S think of as a starting point. Okay, so imagine the system starts in an outcome S, so everyone's picked a single path, for example. And on the left-hand side, I entangle S and S star by considering all unilateral deviations from S by a single player to what that player is doing in this totally different outcome S star. Okay, so the notation here for a fixed I is player I picks its S star strategy. The other n-1 players pick their S strategies. Okay, so this is like starting from S, and player I only deviates to its S star strategy. Now, starting from S, there are n players. I can have n different unilateral deviations, so that gives me n summands. And each time I look at the cost of the deviating player following the summand, which is starting to sound like it has something to do with Nash equilibria, and it will. I'll show you on the next slide. Okay? But anyways, this is just what it is. So on the left-hand side, you have a sum of n things. Starting from S, you look at unilateral deviations to S star. You look at those players' incurred costs. Now, what does smoothness require? It requires I can disentangle S and S star. I can charge the cost on the left to the costs of S and S star individually, and lambda and mu are just the charging factors that I incur. Okay, so again, lambda think of as bigger than 1 generally, something like 2. Mu think of as less than 1, something like 1/2. Okay, so say twice S star plus half times cost of S. Think of S as the start, and then you're moving it in one dimension toward S star. Right, so
the start cost should enter less into your form.
Exactly. And it'll be really obvious why why the asymmetry on the next slide. So what's not, so to be honest, what did I promise this definition was supposed to do? The very first thing I said, sufficient condition on the upper bound, for an upper bound on the price of anarchy. Even that, it's not at all obvious what this has to do with it, okay? But it turns out it takes only about 3 lines to show you what it has to do with it. So let me show you the 3 lines. Xinguang. Let me show you. So basically what you're doing is you're charging a Nash equilibrium back to itself. And that's why you need a mu less than 1. Okay? So, but let me actually just show you the argument. Okay? So claim, all right, if a game is smooth, then it has a bounded price of anarchy. Okay? And it turns out the parameters lambda and mu give you an upper bound of the price of anarchy of lambda over 1 minus mu. So if lambda was 2 and mu was a half, then you're going to get 2 over a half. That will give you an upper bound of 4. Okay? So let me show you why this is true. Mu better be less than 1.
So I see. So you will have a hard time producing mu equals 1/2 and lambda equals 1/3.
So think of lambda as like 2.
Right.
Yeah.
You didn't ask it because then one.
That's true. But they basically, the game will simply not be smooth for those values of the parameters. Yeah. So I mean, this will sort of show that, the fact that this has a connection to the price of anarchy will imply certain constraints on lambda and mu. But I'm going to leave those implicit. Okay. All right, good. So all right, so what are we going to do? So we're trying to prove an upper bound on the price of anarchy. Remember what that means? That means you take an arbitrary equilibrium. If there's many, it has to apply to all of them. You take any equilibrium, you say it's not much more expensive than an optimal solution. That's what it means. So we're going to prove that, okay, for a smooth game. S is an equilibrium, S star is an optimal solution. Now, if you think about it, I haven't told you anything about this game at all, right? We have 3 hypotheses and nothing else. So the only thing we could possibly do is produce a 3-line proof, basically. So let's just follow our nose and do it. There's really a unique thing that could possibly work. What do we know? We know S is a Nash equilibrium. We better use that. We're not going to be able to prove something about an arbitrary outcome. I promised you that it was important the objective is a sum objective. We better use that. And of course, we better use that the game is smooth. So let's just invoke them one at a time. Here's a 3-line proof. So you start with equilibrium and its cost. Okay? So we know what the objective function is. It's the sum of the player's costs. Fine. Now let's use that S is a Nash equilibrium. What does that mean? Unilateral deviations only increase the deviator's cost. In particular, if a player deviates to what we wish it was doing in the optimal solution, that particular deviation will only increase its cost. Okay? So that's what I've done here. For each player I do a thought experiment of it switching to its S star strategy. That's one particular deviation. Things only get worse for that player. And now, of course, smoothness applies. Right? Smoothness exactly says I can disentangle this sum, charge it against lambda times the optimal solution. That's why it's not surprising lambda is bigger than 1, plus mu back times the cost of the equilibrium solution. Okay? And because I'm charging back to what I started with, this better be less than 1. I subtract this on the left-hand side, divide through, and what do you get? You get that every equilibrium is the most lambda for 1 minus mu times the optimal cost, S star. Okay? Yeah. Excellent. Excellent. So Shenghua is just basically said the most important point for the first kind of half of the talk, right? So, because initially you look at this and you're like, this definition is vacuous, right? This is really the same thing as proving an upper bound on the price of anarchy. But actually it's not, okay? If we revisit the smoothness definition, let me show you what that is. So actually what we required in the definition of smoothness is a little bit stronger than what we actually just used to bound the price of anarchy. And it's that little bit of extra strength which is going to give us the automatic robustness. So why is it stronger? Why is it stronger? Well, if you look at that derivation, okay, so smoothness was used in this final inequality, okay, to disentangle these two things. And actually we knew that the starting point was an equilibrium and S star was an optimum. But in particular, we knew that S was a Nash equilibrium. So if we had wanted to, we could have used in the hypothesis that S was a Nash equilibrium in deriving this final inequality. Now, it's not clear we need to. We've already used the equilibrium hypothesis to get this far. But it's still an equilibrium. We can use it again to derive this if we want. Okay? Smoothness says, no. You better be able to not just disentangle equilibria, but actually you can do that exact same disentangling for every single pair of outcomes S and S star, equilibrium or not. Okay? So that's the sense in which it maybe even seems like an odd definition. It just seems like a definition where I just sort of threw in some extra stuff. I made my life harder, and I haven't shown you any benefit of it. But I just want you to appreciate that for now. Okay? Smoothness is strictly stronger than what was required for that derivation. So that's why I call it a sufficient condition for an upper bound. Okay? All right. Good question. So it depends on the context. There are contexts in which it's not strictly stronger, and that'll be my last theorem. Okay? There are certainly contexts in which it is strictly stronger. So I think I think that general issue is actually a very interesting now research direction. When are they the same and when are they different? Okay? But again, the last theorem will be a sense in which you can prove a converse. Okay? All right, so what? So I showed you a definition which is strictly stronger, right? Why is it useful? What does it buy you? You know, I've just made our life harder. What benefit do you get if you meet this more stringent definition? Okay, so there's actually a lot of applications. I'm only going to single out one in the interest of time, maybe my favorite, which is about no-regret sequences. So there's a definition here. I'll go through it in a second. But I mean, maybe I just want to say what is the point that this is trying to make. So, you know, so the usual definition of a price of anarchy guarantee, the interpretation says, oh, as long as your system is at equilibrium, you know, it doesn't matter which one you're at. This promises that your performance is good. Okay, but it's a non-trivial hypothesis if your system is at equilibrium, especially now that Costas has done us the favor of showing us how hard it is to compute equilibria in many contexts, right? Some games it's easy for players to learn equilibria. Some games it's not. But the fact that it's not always easy is a legitimate critique about the usual price of anarchy. Okay, does that upper bound have meaning if it cannot be reached? So that motivates, okay, the research direction of weakening the rationality required of the participants in the system and still having a meaningful guarantee. Okay, so you'd like to say even if you're not at equilibrium in some sense, you still get a good bound. You still get an approximation guarantee with respect to optimal. Now, of course, this is now a modeling quandary, right? Because, you know, in any kind of interesting game, like consider a routing game where we have a link which is like a billion, right? So there's no way you're going to prove a guarantee on every possible non-equilibrium outcome. What if everyone's on the billion link for no good reason? Okay, it's going to be arbitrarily worse than everything. So we need some intermediate ground. Okay, you haven't converged to an equilibrium, but at least players are trying in some sense. Okay, they're making some effort to not do something ridiculous. There's actually a number of ways to make that precise, formal definitions one could propose, and actually there'll be analogous theorems for many of those proposals. So I want to point out, I'm really just singling out one example. Okay, so for my purposes, no regret is a really nice, very popular definition of what it means for a system to not necessarily be converging to anything, but you still have players with reasonable behavior. Okay, so what's the definition? So basically what it's roughly speaking kind of says, now instead of a single outcome, we look at a sequence of outcomes, which you might want to interpret as being a bunch of players groping toward an equilibrium over time. So they're trying to converge, but they've failed. And roughly it says you at least have some Nash equilibrium-like conditions on average over time on this sequence. So precisely, you look at any given player I. Okay, so it played in some way over the sequence. It got some cost. So these are different traffic patterns, say, possibly very differently in traffic patterns. You look at the average time it took you to get from S to T over this sequence. That's some average cost. And you better have at least done as well as the best non-adaptive strategy. Okay, so the strategy which didn't try to do any learning at all. Just sort of picked the path, ignored the traffic patterns it was seeing, and just used it every day. Okay, so that's what no regret is by definition. Okay, so your average cost trying to adapt to the system is as good as any non-adaptive policy for playing the game over and over. Okay, so that's the definition of no regret. You know, my sense is that, you know, in the learning community and in the game theory community, you know, this is roughly identified that if you have players who are seriously trying to play a game, you're likely to be at no regret. Okay, that somehow if you have actual, you know, purposeful learning, the sequence you expect to have the no regret condition. A way to back that up mathematically is you can prove things like, well, as long as everybody uses a sort of, you know, simple randomized, you know, off-the-shelf hedging algorithm, you can actually guarantee even in the worst case no regret. But of course no regret may arise even if players are doing something other than using a guaranteed no regret algorithm. Okay? But again, you know, intuitively or qualitatively this is a reasonable model of out of equilibrium behavior, and a theorem which I'll show you proof on the next slide is that if you're smooth, not only do you have a lambda over 1 minus mu guarantee for equilibria, every single no regret sequence obeys exactly the same bound. And I want to emphasize, I wish I had examples of this, but I don't. It's really much more general to bound all no regret sequences than all Nash equilibria. A particular special case of a Nash equilibrium or of a no regret sequence is you just play the same equilibrium over and over and over again. It's very easy to see that that has no regret. But in general, it's easy to exhibit, even in very simple games, seemingly oscillatory trajectories that nevertheless satisfy the no regret sequence. And this theorem says exactly the same bound holds. Exactly the same bound.
I'm not familiar with the thing. It usually takes time to absorb anything. But no, the first bullet here.
Yeah.
So your cost is no worse than playing Q every time. What do the others do?
The same thing.
The same thing as
They did before.
QI? Oh, they did before without me.
So
If I play always QI, why should they do the same thing themselves?
oh yeah, you might get a completely different trajectory. So that's just not.
So therefore, isn't it best comparing apples and oranges?
Uh,
On one side you say, look, I might as well have played QI, but if I played QI, they would have done something else.
Sure.
Then what is the meaningful of comparing
Well, I mean, you'd have to reason about how other people would respond. Okay, so
That is not captured by the book.
absolutely, no, that's a legitimate objection. I mean, so there's a number of ways to interpret this. One way to interpret this is it's basically the same as coarse correlated equilibria. So if you look at the sort of average frequency of play over this trajectory, it's basically saying, well, at the very least, okay, so one fact is, so I said a Nash equilibrium is a special case of this where you repeat it over and over again. If you take any mixed Nash equilibrium and you just sample from it, you're going to get a no regret sequence in the limit. In fact, if you take any correlated equilibrium and you repeat it, you're going to get this in the limit. And there's even a bigger set than correlated equilibria called coarse correlated equilibria. So, I mean, one interpretation would just be, I mean, this at least says that people are doing as good as the worst correlated equilibrium. In fact, it's the worst even coarse correlated equilibrium, which is a bigger set. So for my purposes, I am less interested in this being a faithful model of how people reason about their behavior. That is not the point of this definition for my purposes. The purpose for this talk is this is a really big sequence of outcomes, and this bound in the price of anarchy holds for all of them. If you like this definition, because of the behavioral interpretation, fine. If you like it because it's at least all correlated equilibria, fine. If you don't like it, that's also fine, because there are other definitions for which analogous theorems also hold. Okay? So by no envy, you mean? So I guess in general, I'm not thinking about symmetric games. So the action sets could be different. So like think about routing games where people have different origins and destinations. Then I'm not even sure how to define it. Yeah. So for symmetric games, I think it would be, again, there's a little trickiness there where there might be a sort of zero cost link that nobody ever bothered to use. So I think there's a technical issue with if you just have no envy. But anyways, it's pretty robust is what I'm trying to say. So the theorem is definitely not particular to the no regret definition. There are many other definitions of out-of-equilibrium behavior for which you can have analogous theorem. I just wanted to single one out. But yeah, it's a completely legitimate objection of the definition. Other questions? Okay. So, yeah. Yeah, so it actually also works for that. So, you need some extra assumptions. So that's for potential games. So basically, the problem is if you do best response, it need not converge, which is fine. I'm not actually, I don't actually care about convergence. There actually are counterexamples if you don't have a potential, where your best response can actually cycle in nasty outcomes. Now, you might think it's, oh, well, why is he even talking about potential games? You know it converges. You know it converges to a pure strategy Nash equilibria. So obviously, all the usual bounds for pure equilibria will hold. So what does hold is if you have a potential, but you abort best response dynamics really early, like after, say, quasi-linear number of steps, as opposed to letting it go for an exponential number of steps, which is generally how much you need per converge to converge to an exact equilibrium, then it turns out smoothness immediately implies lambda over 1 minus mu plus an epsilon, depending on the sequence length, even if you truncate after very few iterations. So there are interesting implications for best response dynamics in potential games. And there are counterexamples for best response dynamics outside of potential games. Yeah.
Typically get kind of the balance you like to the smoothness. So you've already proven
That's theorem 2. So that's exactly, so Christian asked the question, is there a converse? And that's exactly what the second part of the talk is about. Yeah, it's a good question. So the short answer is yes. Yeah. Okay. So in fact, once it occurs to you to try this definition of smoothness and the fact that these kinds of results might be true, the proofs just write themselves, and you will see this. Okay. So I will prove that last theorem to you just on this slide. Okay. So what am I trying to prove? I'm trying to prove that if your game is smooth, actually all no regret sequences are just as good as equilibria. Okay. So why is that true? Well, again, let's just follow our nose. Okay, it's just going to work. The obvious thing to do just works. So what's our hypothesis now? It's not that we have a single outcome which is an equilibrium. It's that we have a sequence of outcomes which is no regret. Okay? So our hypothesis is different, and I want to emphasize this. We know absolutely nothing about any individual outcome S sub t in the sequence. Okay, so you think of 1,000 days, a bunch of different traffic patterns. Some of these traffic patterns might be wretched. Okay? All of the players might just be having horrible costs. Okay? But the no regret guarantee says on average, people are doing as well as any non-adaptive strategy. Okay? So that's our new hypothesis. We have a sequence, which in this aggregate sense is no regret. S star is an optimal solution. Of course, that doesn't depend on what day. It's the same game being played over and over again. So we're interested in the average cost over this sequence. Let's just, I'm going to normalize by capital T only at the end. So let's just look at the sum of the costs. What was the first step in our previous derivation? Well, we said, oh, we have a sum objective. Okay, so what is our objective function? It's the sum of the players of how much player I, what the cost they incur at time t. Now the next step is the one where we seem like we're in trouble, right? Because the next line in the previous derivation, we invoked the Nash equilibrium condition. We said if somebody deviates from their equilibrium strategy to their S star strategy, their cost only gets worse. And that's clearly wrong, right? Because just because there's no regret sequence does not mean any of those are equilibria. Okay, they can all be non-equilibria. Okay, remember, we only have this aggregate hypothesis over the sequence. So let me defer the issue with some notation called delta. Delta is if we think about a player I at time t switching from its S strategy, which need not be best response, to its S star strategy, this is how much its cost drops. Okay? Now, if it was in equilibrium, we know this is non-positive, right? It doesn't drop at all, it goes up. If it's not in equilibrium, this might be positive. Okay? So delta is how much you get better at day t by switching to your S star strategy. Okay? Now, so this is just what I said. Now it's sort of clear what happens, right? Smoothness will allow us to control this first group of terms. No regret will allow us to control the second group of terms, and it just works. What do I mean it just works? Well, let's deal with the first part. Here, I've collected the deltas for sort of, subsequent dealing with over here. Now, so I want to do the disentangling, right? What do I know about ST? Nothing. What does smoothness allow me to disentangle? Everything. So it's exactly what I need in this context, right? So I know nothing about S sub t, but smoothness allows me to charge this sum against lambda times the optimal cost, which is independent of t, plus mu back times the cost of st again. Okay? What is the meaning of no regret? No regret means that on average there is no non-adaptive policy, which makes you better off. In particular, the non-adaptive policy of playing S star every time does not help you. Okay? What does that mean mathematically? It means that the sum of these deltas for any fixed player I over the whole sequence is non-positive. So I can throw those away, divide through by t, and move this back over, and I get what I want. Average cost over the sequence is lambda over 1 minus mu times the cost of the optimal solution. And that's it. Questions about that? So there's lots of other implications of smoothness. All of the proofs have roughly the same length, sometimes a little bit longer, 2 slides, not 1. Okay? But again, the implications turn out to be, they really write themselves once you have the definition in place. So a couple of things. So part of this is my answer to Silvio's question, which is another reason to care about no regret sequences is that, if you think about a no regret sequence as inducing mixed distributions by just looking at the frequency of play of the different players, you can interpret that as mixed strategies, which are even more general than mixed Nash. So every mixed Nash gives rise to a no regret sequence. Similarly, correlated equilibria, for those of you who know what it is, it's even more general. It's called coarse correlated equilibria usually, or the Hanen set sometimes. In the learning theory context. So you have this hierarchy of equilibrium concepts. No regret sequences corresponds to the biggest set of them all, and that's what we just upper bounded. Okay, so that's interesting. Also, I want to mention that the first researchers to propose thinking about no regret in a price of anarchy context include Aaron Roth, who of course all of you know, Avram Blum, Ayal Evandar, Katrina Leggett, and Mohammed Hajjagayi. They had a couple of very nice papers in Podzi and Stock. They both proposed thinking about no regret in this context, and also they proved special cases, a number of special cases, some of the theorems I'm going to state later. Okay? All right. So again, the no regret one is the only one I'm going to talk about. I guess in my answer to Christian, I mentioned this thing about best response dynamics. There's other applications as well. So for example, if you look at approximate Nash equilibria, the bound you get from smoothness degrades exactly how you'd want as a function of the equilibrium approximation parameter. Also, there's implications for Bayes-Nash equilibria, which I don't have up here. And again, the point is, if you derive a bound using smoothness, maybe you were only caring about this middle, this intersection of all of these, of pure Nash equilibria. But again, automatically, whatever number you prove, 5/2 or whatever, applies to the union of all 6 of these sets. Do you have a question there?
You were talking about like best response dynamics. You have to kind of rule out, like, imagine a graph with 2 edges, and each day we both go on the top. Then we both best respond and switch to the bottom.
Yeah, it's asynchronous. It's an asynchronous model. Players move one at a time. It's a good question. I haven't thought about, I mean, there should be a version which has a much weaker, which allows some kind of synchrony that's reasonable. Yeah, you need some condition. You would need, you need a non-vacuous condition, but there should be a version that allows synchronous moves, some form of synchronous moves. But I haven't thought about that. That's a good comment. Yeah, so the best response dynamics here refers to where one player moves at each time, and then everybody sees the updated system. I mean, you can imagine versions where you allow stale information and this kind of stuff, but I haven't thought about it. Okay, so so the worry, and this is, or at least, for the skeptics out there, and if I was out there, I'd probably be one of them, it says, well, if this definition is so good, if it has so many nice implications, probably nothing meets it. Right? Probably it's sort of it's very hard to find an example of the smoothness thing if it gives you so many things for free. But actually, so when I first formulated the definition, I had no idea if it was useful. I was like, it's a definition. But definitions are cheap, right? I mean, anyone can invent one. So I sort of empirically tried to figure out if it was going to be good for anything. So I took some of my, I looked up some of my favorite price of anarchy analyses, and I said, well, is anyone actually doing a smoothness guarantee inadvertently? And I was shocked that, the first K for K pretty large, like half dozen or something. Either the analysis was patently a smoothness argument, or it could be reasonably easily rephrased as a smoothness argument. So in other words, what I'm trying to say is the way the community has been proving bounds on the price of anarchy all along anyways has been using smoothness guarantees. So certainly for every talk you've ever seen me give, probably for most of the talks you've ever seen, or sort of 90% of the other talks you've ever seen on the price of anarchy, it is a smoothness guarantee, and ergo, whatever number was stated applies to the union of all 6 of those sets, just by that first main theorem. Okay, so just automatically. A couple examples, and again, these are just chosen from a much larger set to give you some flavor of the kind of numbers you see. So let's just think about routing games. Just to keep it simple, let's think about the affine case. So cost functions are ax plus b. For different cost functions, you get different numbers, okay, different constants. But say the affine case, so like the example I showed you on slide 3. So in 2 parallel independent Stocko 5 papers, Auerbach, Azar, and Epstein, especially Christodoulou and Koutsoupis, it's especially obvious, they're really just proving smoothness. And what they prove is that every atomic selfish routing game with affine cost functions is smooth with the parameters lambda equals 5/3, mu equals 1/3. The bound, remember, is lambda over 1 minus mu. So here you can get 5/3 over 2/3 or 5/2. Okay? They also prove, both of these sets of authors prove that the lower bound of 5/2. And they were only interested in pure equilibria, so they showed that even pure equilibria can be off by a factor of 2.5. Okay? So you can also think about the non-atomic case. So this is what some of you may have seen me talk about a lot several years ago. So this is where you have an infinite number of players. So flow is fractional, and you're thinking about drivers on the highway or packets in a network. And so again, it's sort of implicit in my early work with Ava. It's even more explicit in some different proofs of those results by Coria, Schulz, and Stier-Moses, that's really just smoothness too. You get different numbers in the non-atomic case, in the sort of infinite player case than the atomic case. So for example, in the affine case, you get lambda equals 1 and mu equals 1/4. Again, lambda over 1 minus mu, you're going to get 4/3. And again, in this context, even if you care about sort of, the proper meaning of pure equilibria in this non-atomic case, Ava and I already showed that 4/3 is a lower bound. Okay? So, and I want to emphasize it's not just about routing games. So there are games about facility location, games about resource allocation. Again, you can look at them and say, oh, this is really just a smoothness argument. And really what the author was doing was determining the optimal values of lambda and mu to get a tight bound on the price of anarchy. Okay? Yep.
Do you think it's a good idea to let anarchists play atomic games?
Is that your joke originally? Okay. Oh yeah, no. I'm sure we could all tell Adam's stories till the cow comes home. So. Okay. Okay, I'm not going to talk about this. So the point is really the crux of all these price of anarchy analyses is to figure out the optimal smoothness bound, and that is usually the hard part of any of these analyses. The one point I want to make is that in most of the sort of most well-known analyses, it's a little technical in that you have to sort of write down a few inequalities, but it's not like it's long, okay, in most of the most common cases. So, it's sort of mucking about with inequalities, but the final proof is often a half a page or a page. Okay, so certainly those 2 examples on the last slide, that's true. So this, for example, is a full proof of the smoothness guarantee that Christodoulou and Koutsoupis proof for the atomic case. So, okay, so you got to work it out. You got to figure out what are the optimal constants to use, but you can do it in many cases of interest. Okay. All right. So, good. So now I want to at least get to stating the second result. Okay, so the first result just says smoothness implies all this other good stuff with exactly the same bound. And now this is to answer both Christian's question and Adam's question, which basically says, do you lose anything by confining yourself to a smoothness approach to bounding the price of anarchy. Okay, so what do we observe right away? We observe that it's requiring more, right? I need you to disentangle not just Equilibria, but everything. I've showed you some good news that if you succeed in doing that, you get all this other stuff for free. But you might be worried you could prove a really low number just for Equilibria, and then if you want it for all these 6 big sets, you have to deal with some much bigger, higher number. And sort of motivated by examples like these and many of the other ones I found when I was randomly sampling the literature, what sort of shocked me, so let's just think about this bottom example of atomic selfish routing games, right? So again, Christodoulou and Koutsoupis weren't even worried about mixed Equilibria, correlated Equilibria, or anything. They were just trying to figure out the pure bound, and they nailed it at 5/2. In particular, they have a lower bound just for pure Equilibria, which is 2.5. And the theory I already just showed you says that that 2.5 extends automatically to the union of all of these. Okay, so there's an upper bound on everything. So of course, the wider class of outcomes you're proving upper bounds for, that upper bound is only going to get worse. It's only going to get bigger. But I showed a matching upper bound on the union of these sets and a lower bound just in the smallest set. So in other words, from a worst case approximation perspective, this whole hierarchy just collapses. You get exactly the same worst case approximation factor no matter which set you're looking at. All right, when you might expect, and certainly, in a single game, in general, you will see a hierarchy. Okay, if I just gave you a single routing game, this one network, generally the worst mixed Nash will be worse than the worst pure, worst correlated will be worse than the worst mixed, and so on. But if you do worst case analysis over some natural class of games, it just collapses. Exactly the same number for all of the sets. And so I was wondering, I asked the same question that you guys did, which is, is there something fundamental about this collapse? Is it possible you could formulate a theorem which kind of says the collapse is always going to happen? In other words, while it's a strictly stronger condition smoothness, for worst case approximation, there's no loss of generality in restricting yourself to a smoothness argument. Okay, so what would that even mean to prove that? Well, here's what I came up with. Came up with the following theorem, and this is not as general as the previous stuff, but so when I say congestion games, just think of routing games, okay? But for all atomic routing games, you can prove you never lose anything by confining yourself to a smoothness guarantee. You always get exactly the right number, even if you only cared about pure Equilibria and none of those other bigger sets. You always get the right number. There's always a collapse in all of those sets. How do you say that? Here's how you say that, okay? So first of all, one thing about these routing games you have to realize is that the number you get, the price of anarchy, depends on the cost functions. Okay, so if 2.5 is the right answer for affine cost, if I switch it to quadratic costs, I get some different constant. I get 4 or something. Cubic costs, I get 7. Okay, so depending on how convex, how nonlinear these cost functions are, you get different numbers. So the way I'm going to state this is I'm going to parameterize routing games by what cost functions I'm permitted to place on all of those links. Okay, and depending on what cost functions I use, I'll get different numbers. Okay, but just fix any arbitrary set of cost functions. Maybe the linear functions, maybe C is quadratic functions, maybe it's a finite set of your favorite 17 functions. I just don't care. Okay, any cost set function at all. Now on the right-hand side, what do we have? The meaning of the right-hand side is the tightest upper bound you're going to be able to prove on the price of anarchy if I force you to use a smoothness approach. Okay? So what does that mean? You take the minimum over all valid smoothness parameters lambda and mu, okay, all pairs lambda and mu such that every game, every routing game with cost functions in C is lambda mu smooth. So again, C is fixed. Depending on C, you'll get different lambda and mu, but for fixed C, there'll be some lambda mu.
So lambda and mu functions.
Exactly. Exactly. Yeah, exactly. So the number you get here and the number you get here is going to depend on C. But if you like, think of C as, like bounded degree polynomials with nonlinear coefficients, say, okay? So think of it as a finite set. It doesn't matter, but it's fixed.
Figure out what lambda and mu of a given C are.
Good question. So you can figure it out enough to prove this theorem, which is which is already the meat of this proof. Now, if you really wanted numbers, if you want a closed form formula, it's usually not so easy. It's been done previously for polynomials. I'll give you the references in a second. You can do it in numeric, so the proof allows you to evaluate it numerically quite well for many sets. So that's the good news, okay? It's a good question. But for now, think of this theorem as just conceptual, okay? That's how I want you to interpret this right now. So again, right-hand side, the best upper bound you're ever going to get using a smoothness approach. Okay, so you look at all parameters which are actually smooth for this class of games. This class of games is routing games with cost functions in C, right? So the upper bound you get is lambda over 1 minus mu, so of course that's what I minimize over all choices of smoothness parameters. The left-hand side is the right answer if you only care about pure Equilibria. okay? Meaning, find me a worst case example, right? You're allowed to invent any routing game with cost functions in C. Okay, again, there's millions of them. There's an infinite number, obviously. Find me the worst. Find me the one with the largest pure price of anarchy, okay? What I proved to you on slide 4 was weak duality, the fact that this inequality certainly holds, right? On slide 4, I proved to you that for any valid smoothness parameters, lambda and mu, lambda over 1 minus mu is a valid upper bound on the, in particular, the price of anarchy of pure equilibria of every game in that class. So weak duality is certainly true. Yeah, so C is fixed, but arbitrary.
C could be in particular a single cost function.
That's right.
So that implies in particular that for every single cost function.
That's right. That's right. So the theorem asserts strong duality, quote unquote. I mean this as a metaphor, not technically. It asserts that equality will hold. Okay? You can find on the one hand a pair of smoothness parameters lambda and mu, and on the other hand a routing game with cost functions in C, and a Nash equilibrium with that routing game, which is off by a factor of lambda over 1 minus mu, okay, for that same set of parameters. Okay? So that's what the theorem states. Any more questions about what it says? Okay, again, the interpretation here is at least for routing games, you will never lose out by restricting yourself to a smoothness argument. Okay, so this is the sense in which there is a converse. To answer Christian's question, actually smoothness is without loss of generality. Okay. There are, of course, proofs which are not smoothness proofs, but they'll never give you a better answer than some other smoothness proof.
Obviously, the fact that you're stating the theorem this way means that there's examples of graphs where on those particular graphs, the left-hand side is...
Right, so I'm not really interpreting this bottom picture for you. So basically, yeah, so I mean, so there should be this hierarchy, right? So in a given game, there's going to be this hierarchy between these different, this sort of you know, family of sets. But what this sort of says is, you know, you can always find a worst case. So basically, in every worst case example, everything's going to be exactly the same factor, 5/2 or whatever, away from the optimal. Okay, so again, this is that sort of collapse of all of those sets. No. So this is just for pure, which is sort of the lowest of all of them. It's sort of the smallest lower bound. But if yeah. So anyways, okay. So any questions about what this says? All right. So I'm nearly out of time. Let me make maybe one comment. So this theorem requires some work. I'm not going to say a lot about it. But let me make maybe one comment about the right-hand side. One comment about the left-hand side. Okay, I only have 3 more slides actually, but I'll leave it to you to ask questions for the rest of the time, and I'm happy to take them. So, but let me just make one comment on each of the 2 sides anyway. So 1 slide on each. So to prove this, so how do you prove this equality? So we really need to actually understand the right-hand side a little bit, because this is sort of Jennifer's question, which is, you know, what on earth is this thing? I mean, this is such an abstract optimization problem. It just seems like you can't get any handle on it. But actually, you can reason about this. So what can I say? So the idea is to just apply kind of optimization theory to this right-hand side and see what you can figure out. Now, what do we have going for us? Okay, there's 2 main things we have going for us. The first is there's only 2 parameters, right? There's only 2 things we're searching over, the parameter lambda and the parameter mu. So this is an optimization problem which is fundamentally in the plane. So that already makes at least me feel a little bit more comfortable, like, you know, maybe how bad could it be? So we have 2 decision variables. Now, what about the feasible region? This is what seems more scary, right? So lambda mu such that all such games are lambda mu smooth. All right. So what is this? What kind of constraint does this place on the parameters lambda and mu? But actually, it's not that bad. In the sense that really what it is it's just a bunch of half planes. I mean, it's an infinite number of half planes. There's a lot of half planes. But all the smoothness constraints are linear in lambda and mu. What does it say? It says for some given game from this class, right, routing games with some cost functions, some outcome S star, some fixed constant, right, this depends on nothing, is almost lambda, one of our decision variables, times some fixed constant, plus mu, our other decision variable, times some other fixed constant, right? So this is a half plane. That's all, okay? So in other words, well, actually, I guess that's a slide. So what we're trying to do is we're trying to minimize lambda over 1 minus mu in the plane with respect to a polytope, roughly, intersection of a whole bunch of half planes. Now, lambda over 1 minus mu is not a linear function. It may look funky at first, but it's decreasing in lambda, it's decreasing in mu, if you think about it. So you want to optimize this, you go southwest as far as you can in this feasible region. Okay? So what does that mean? That means the optimal solution is just going to be defined by the intersection of two of these hyperplanes, two of these half spaces. Okay? So there's a very succinct summary of what this optimal solution lambda and mu is. Okay? It corresponds to two different smoothness constraints. All right? So that's the main idea. So that's the main idea of understanding the right-hand side. Now, how do you take this data? Okay, now what you got to do, right? Now we have to actually construct a routing game with these cost functions where the price of anarchy is as big as lambda over 1 minus mu. Okay, where lambda and mu come from these two hyperplanes. I apologize, this is going to be very sketchy, but the idea is you have a network where basically you have two cycles. Okay, why do you have two cycles? One cycle for each of the two hyperplanes. Okay, it turns out that's what you need. Now, the form of the bad equilibrium, so you have lots of players, and they each go around the cycle. And they have to pick either to go around a cycle a long way or a short way. And in the bad equilibrium, they go around each cycle the long way. That causes more congestion because their paths have more hops. In the optimal solution, everybody goes around the cycle the short way. Again, that causes much less congestion. And it turns out if you set the cost functions correctly, you can match it up so that the gap you get exactly matches the sort of signatures of those two hyperplanes, the signatures of those two smoothness constraints. Okay? And that's technical, and I'm not going to have time for it. But that's the flavor of it. Okay? Figure out the two hyperplanes, use those as ingredients to build this double cycle network, which achieves the corresponding lambda over 1 minus mu with equality. All right, so what I actually more want to talk about is a couple corollaries that fall out of the proof, which I like. And again, this is more now specific to routing games. It's not as general as the first part of the talk, but still. So there's two interesting implications for atomic routing games. The first is the first characterization of what worst case examples look like for the price of anarchy in atomic routing games. So some of you may have seen me several years ago talk about a theorem which gave an analogous characterization for the non-atomic case, where you have a large population of players. In particular, there's a theorem which says, again, with the same flavor, fix a class of cost functions. Now, hypothetically, think about searching over all networks in the world and all traffic matrices, trying to find the largest price of anarchy you're ever going to see. There's a theorem which says, actually, that supremum will always be attained in trivial networks with only two nodes and two links. Okay? So among all multi-commodity networks for fixed cost functions, the worst case price of anarchy is always attained in two-node, two-link networks. So that's kind of a short certificate, universally, of what worst case examples are for the price of anarchy in the non-atomic case. So there was never an analog of that theorem for the atomic case, and this proof gives one. Worst case examples are necessarily more complicated. Okay, so there's necessary and sufficient conditions here. Basically, instead of two parallel links, you need two parallel cycles. And those are generally necessary and sufficient to get the worst case price of anarchy in the atomic case with respect to a given class of cost functions. There is no bound on the size of the cycles. So, I mean, again, so basically the reason is, these cost functions could be anything. So the cost functions might well be 0 up to some hundreds of numbers of players. And then I'm going to need to have hundreds of players going across cycles of length 100 just to expose the non-trivial part of the cost function. So for reasonable cost functions, the cycles are going to be reasonable. But at the level of abstraction I stated the theorem, there's no way to bound the size of those cycles. Okay. So all it is, it really just says two cycles of suitable length. Okay. And again, it's necessary and sufficient. That's a good question. And then in particular, and this parallels the non-atomic work, once you know what the worst case examples look like, you also understand what the worst case price of anarchy is. And so in particular, there were no analyses outside of polynomial cost functions at all in the atomic case. And this is what I think of as a complete solution to what is the tight price of anarchy bound for atomic routing, no matter what the cost functions are, polynomials or not. Okay. So let me just wrap up again. What are the takeaways? So the community was already, it turns out, proving price of anarchy guarantees in a very particular structured way. So I gave you a definition which formalized what is that canonical proof template. And we observed that anything proved using that template has many more implications. No regret sequences is what I highlighted. Lots of other stuff too, approximate Nash equilibria, correlated equilibria, best response dynamics. And I showed you at least for the special case of routing games, which I already think are quite fundamental, you don't actually lose anything using smoothness, and you can formulate that as a theorem. Okay, so the way I describe this is when you have that strong duality, I say that's a tight class of games. You're guaranteed to lose nothing from smoothness. I think there will be other classes of tight games, but I leave that as an open question. Thanks very much. I mean, conceivably. So, I mean, the flavor here is you always have an equilibrium concept and you do worst case analysis over that equilibrium concept. So I'd be a little hesitant to study anything for which Nash equilibria was not a subset.
I mean, if you
So,
look at your first example,
yeah.
in one case they both got 14, in the
Right.
other case one got 14 and the other got 10. So I can imagine some players that are very reasonable sort of saying, well, let's go for 14 and 10.
And are you willing to have a model which says it's impossible they'll both be at the Nash equilibrium?
What? No, I mean maybe in some repeated game they make a deal on even basis.
Right, yeah, no, but
So they should, they're cooperative players.
I guess what I'm trying to point out is there's two distinct modeling decisions here. One is what is the set of all imaginable outcomes we're going to accept, okay? And the second modeling decision is there's multiplicity, which one do we use to determine our approximation ratio? And so if you wanted to beat the price of anarchy, you would either have to, in the first step, take something which excludes some Nash equilibria, or in the second step you'd have to do something other than take the worst case. So I was trying to get at which of the two you were sort of proposing. Yeah, no, I mean, that would be an interesting direction. So, yeah, so this is really trying to go the conservative approach. Okay, so what guarantees can you make assuming nothing about the reasonableness of the players? So that would give you different answers. So something else, yeah. So. Yeah, Ron.
I'm not sure if this question makes sense, but if you allow the players to play mixed strategies,
Yeah.
does all this carry over?
It does, actually. So that was one of the smaller sets, actually, in the here. So here's the mixed Nash here, actually. Yeah. So which is actually nice, because there was it was actually curious to many of us working here, like whether we really didn't know whether we were going to be finding separations for some interesting domains. And this kind of says you should never expect to see separations. So even though it's definitely a bigger set. And in specific examples, some of these will be worse than some of these. And actually, if I change and again, remember one of my early assumptions, there was a sum objective. If you change that to more like a min-max objective, you do start seeing even worse case separations here. But what this says is some objectives, worst case analysis, you will never see a gap here. That's the interpretation. Could you say it again? So in general, no. Yeah, so even if you just think about the routing context, basically a Byzantine player can sort of clog up the whole network by taking a very long path. So I think what would be interesting would be to have further conditions on top of smoothness, which do guarantee robustness to Byzantine players. And I think there's probably an interesting theorem to be proven there. I think it's actually a very nice question. But at this level of generality, no, it's simply false. There's simply counterexamples.